Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the search ranking system, the engine that decides which results appear first when you type a query into any search box. We'll cover how platforms like Google, Bing, and Amazon take a raw query and return the most relevant results out of billions of documents in under 200 milliseconds. Whether you're preparing for a senior engineering interview or building search infrastructure at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the search ranking system, the engine behind every modern search experience that decides which results appear first and why. If you have ever wondered how Google, Bing, Amazon, or any large-scale search platform takes a raw text query and returns the 10 most relevant results out of billions of documents in under 200 milliseconds, this video is for you. We'll walk through functional requirements, non-functional requirements, the full system architecture, an end-to-end query journey, core ranking models including learning to rank, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FANG interview or building search infrastructure at your company, let's get into it. Here is the core problem. A user types a query into a search box. Behind the scenes, there are billions of documents in the index. The system must instantly understand what the user means, retrieve a candidate set of possibly relevant documents, and then rank those candidates so the best results appear at the top. The ranking cannot just rely on keyword matching because the same word means different things in different contexts. The system must handle freshness, personalization, spam filtering, diversity, and business constraints like ads or policies. If the ranking is wrong, users leave. If it's slow, users leave. If it's biased or spammy, trust erodes. The business needs a search ranking system that combines information retrieval, machine learning, and distributed systems to deliver highly relevant results with sub-second latency at massive scale. Let's walk through the functional requirements. First, the system must accept a user query and return a ranked list of results ordered by relevance. Second, it must support multi-stage ranking, a fast retrieval stage that narrows billions of documents to thousands, followed by a scoring stage that applies expensive machine learning models to re-rank the top candidates. Third, it must incorporate multiple relevance signals including textual relevance, click-through rate, freshness, authority, personalization, and domain-specific features like ratings or price. Fourth, it must support real-time index updates so that new or modified documents appear in search results within minutes, not hours. Fifth, it must provide query understanding capabilities including spell correction, query expansion, synonym handling, and intent classification to improve recall and precision. Now the non-functional requirements. Latency is king. End-to-end search response must be under 200 milliseconds at the 99th percentile, because every additional 100 milliseconds costs measurable engagement. The system must handle tens of thousands of queries per second with horizontal scalability. Availability must be 99.99% because search is the front door of the product. The index must support billions of documents with terabytes of feature data. Ranking quality must be measurable and improvable through A/B testing without downtime. The system must be fault-tolerant. If a shard goes down, degraded results are better than no results. And freshness matters. New content should be searchable within minutes of ingestion. Here is the high-level system architecture. On the left, the query enters through an API gateway and hits the Query Understanding Service, which performs spell correction, tokenization, synonym expansion, and intent classification. The process query then goes to the retrieval layer, which fans out across index shards. Each shard performs inverted index lookup or approximate nearest neighbor search to return candidate documents. These candidates are gathered by a coordinator and passed to the ranking service. The ranking service applies a multi-stage pipeline. A lightweight first-pass scorer filters candidates, then a heavy machine learning model re-ranks the top results. Feature stores provide pre-computed document features and real-time user features. The final ranked list is returned through the API. In parallel, an indexing pipeline continuously processes new documents, computes features, and updates shards. The key metrics to memorize cold. Normalized discounted cumulative gain, or NDCG, measures ranking quality by how well the system places relevant documents at the top positions. Mean reciprocal rank, or MRR, captures how quickly the first relevant result appears. Click-through rate at position 1 tells you whether users find the top result satisfying. Zero result rate measures the fraction of queries that return nothing. Latency at P50 and P99 tracks speed. Query throughput in queries per second measures capacity. Freshness lag measures the time between a document being published and it being searchable. And finally, abandonment rate shows how often users give up without clicking any result. Let's trace the end-to-end query journey. A user on a shopping platform types running shoes for flat feet into the search box. The query understanding service corrects any typos, identifies the intent as product search, and expands the query with synonyms like supportive arch shoes. The retrieval layer fans out to 50 index shards, each returning its top 200 candidates based on BM25 and embedding similarity. The coordinator merges 10,000 candidates and deduplicates. The first pass scorer applies a lightweight gradient-boosted model, using pre-computed features to narrow to 500 candidates. The heavy ranker, a transformer-based cross-encoder, scores these 500 using query document interaction features. Business rules apply. Boost in-stock items, filter out policy violations. The top 20 results are returned to the user in 140 milliseconds. The user clicks the third result and buys the shoes. That click signal feeds back into the training pipeline to improve future rankings. The core models and algorithms. The retrieval stage uses two approaches. Sparse retrieval via BM25 on inverted indexes for exact keyword matching, and dense retrieval via approximate nearest neighbor search on learned embeddings for semantic matching. The ranking stage uses learning to rank, or LTR. Pointwise LTR predicts a relevant score per document. Pairwise LTR, like RankNet or LambdaRank, learns which document should rank higher given a pair. Listwise LTR, like LambdaMart, optimizes the entire ranked list directly. Feature engineering combines query features like length and intent, document features like authority and freshness, and query document interaction features like BM25 score and embedding similarity. Modern systems use deep learning rankers like cross-encoders that jointly encode the query and document for fine-grained relevance matching. The key trade-off is model complexity versus latency. A better model is useless if it cannot score within the latency budget. Now the low-level design deep dive. The inverted index maps each token to a sorted posting list of document IDs with positions and term frequencies. Sharding is done by document ID range, so that each shard holds a complete index for its partition. At query time, the coordinator fans out to all shards in parallel and merges results by score. The feature store is a key value store keyed by document ID, holding pre-computed static features and periodically refresh dynamic features like click-through rate. Real-time features like session context come from a low-latency feature service. The ranking model is served via a model inference service with GPU acceleration, batch scoring, and model versioning for safe rollout. The indexing pipeline processes documents through a tokenizer, feature extractor, and embedding generator before writing to the index. Incremental updates use a write-ahead log and segment merge strategy similar to Lucene. Cache layers at query and result level reduce redundant computation for popular queries. Key takeaways for your interview. First, always describe search ranking as a multi-stage funnel. Retrieval narrows the universe, then progressively more expensive rankers refine the order, because you cannot run a transformer on a billion documents. Second, distinguish sparse retrieval like BM25 from dense retrieval like vector search, and explain why modern systems use both. Third, know learning to rank paradigms pointwise, pairwise, and listwise, and be ready to discuss feature engineering including query, document, and interaction features. Fourth, latency is the hardest constraint. Explain how caching, pre-computation, model distillation, and early termination keep end-to-end response under 200 milliseconds. Fifth, discuss the feedback loop. Clicks and engagement train the ranking model, But naive click data is biased by position, so you need techniques like inverse propensity weighting. If you can articulate these 5 points clearly, you will demonstrate senior-level search system design thinking. That's it for the search ranking system. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the search ranking system. We covered the full picture, from query understanding and multi-stage retrieval, through learning to rank models, feature stores, and the low-level design of the ranking pipeline. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.